All right, here we go, my friends. Put everything away, including your cell phones. We're back in business. All of us, we're in it together. Okay, we're going to start out with talking about types of formulas, and then we'll go back kind of and going over some of the things that we did before break, including like balancing, law of conservation, moles, all that kind of stuff. But moving forward, okay, we're going to start out with two main types. Well, I'll do the first one. I'll just do this one for now. It's called a structural formula. And a structural formula let's spell it right. Formula basically shows us the structure of the molecule. So if I were to draw the structural formula for water, it would look like that. If I were to draw the structural formula for methane, it would look like that. It's actually the picture of what the molecule looks like. That's a structural formula. Okay. There's lots and lots of different terminology for formulas. Structural, just put that out there so that we kind of have that one out of the way. And then we're going to talk about two different types of formulas today called empirical and molecular. And the empirical formula is the formula that has the lowest whole number subscripts. So H2O would be an empirical formula because my subscripts are 2 and 1, and I can't reduce them any further. They're in the lowest whole number ratio. So my ratio of hydrogens to oxygens is 2 to 1. I can't get them any lower. I've got 2 hydrogens for every 1 oxygen. That's an empirical formula. A molecular formula is a formula that shows the exact number of atoms in the molecule. That's a C. I don't know why it looks like an O, but it's a C. Okay. For instance, if I write C2H4O2, it is not lowest whole numbers because 2 to 4 to 2 can be reduced to 1 to 2 to 1. It's telling me that I have 2 carbons, 4 hydrogens, and 2 oxygens. Every molecular formula has one empirical formula. The empirical formula being the lowest whole number ratio. So I'm going to just watching you guys finish writing that down, and I'll show you another example. Let's take this one, CH4. Let's see it. CH4 is an empirical formula. It is also a molecular formula. It is both, because it's telling me I have 1 carbon and 4 hydrogens. If I double this, so it's times 2. I would have 2 carbons and 8 hydrogens. Is that an empirical formula? No. It is only a molecular formula. If I triple it to C3H12, that is only a molecular formula. So I can keep going. I can go times 2, times 3, times 4, times 5. There's only one empirical formula, and a molecular formula is any multiple of that empirical formula, including the first one. This is also a molecular formula. If the compound has 1 carbon and 4 hydrogens, it's methane, it is a molecular formula. So how are you going to know if it's empirical or molecular? Well, all of them are going to be molecular unless they are a salt. Okay, salts are not molecules. They are ionically bonded. Do you remember what an ionic bond is?
Yes.
Okay, an ionically bonded substance like NaCl between a metal and a nonmetal will always be written as empirical. There is no empirical. There are no molecular formulas for a salt. But if you have a molecular formula, like methane or butane or propane or pentane or octane, all of those are going to be molecular formulas because they are molecules, and molecules are covalently bonded, and they will have an empirical formula and they will have molecular formulas. The empirical being the first one and the molecular being any multiple of the first one. Like this guy, C6H12O6. Is that empirical or molecular? Molecular. It's a molecule. Okay, it's a molecule because it is covalently bonded. What is its empirical formula? CH2O1. Right. Just the lowest one is the empirical. So this one's the empirical. There's the molecule. That's its empirical formula. Good? Okay. Now let's take that empirical formula. I'm going to do CH2O. And let's say it weighs 30 grams per mole. That's the gram formula mass. Remember gram formula masses?
Yes.
Okay, carbon, 1 times 12. H, there's 2 times 1. And O, there's 1 times 16. That adds up to 30 grams per mole. So this empirical formula has a gram formula mass of 30. Let's say I have a molecule now, listen to the words, a molecule that has the gram formula mass of 120 grams per mole. What is its molecular formula?
4CH3O4.
Okay, how did he get that? If you know that the lowest one has 30 and the one you're looking for is 120, 120 is 4 times bigger than 30, so my molecule has to be 4 times bigger than this empirical formula. Capiche? Here's another one. CH4. Let's say you have CH4 is the empirical, and you want the molecular formula for the compound that has 128 grams per mole. What is its formula going to be? Well, how much does this bad boy weigh? 16 grams per mole. I want something that weighs 128. 8, perfect. So instead of 1 carbon, you're going to have 8. And instead of 4 hydrogens, you're going to have 8 and 8 is 16, 16, 16, 32, yeah. 32. And that's the molecular formula. Okay? So empirical is the lowest, and molecular is any multiple. And when I talk about the multiple, the atoms get multiplied by that number, and the molar mass or the gram formula mass also goes up by that. Pretty easy, right? Any questions? We lost them.
No, this makes sense. I'm good.
You good? All right. Flip to the back of your reference table now. The fourth formula down on the very back page says percent composition by mass. Okay. Let's say we have a formula. I'm going to do water. Okay, that's the molecule. Its empirical formula is H2O. Okay, that's water. It's also got a molecular formula of H2O. It's a molecule. Okay, and I want to know what the percent of hydrogen in H2O is. So there's a formula there, and it says the percent is going to equal the part over the whole times 100. Isn't that what it says? Mass of part divided by mass of whole times 100. I don't feel like writing out mass of part and mass of whole, so I put a P and a W. Lexi, you alive? All right, welcome back. Okay. The part is going to be the hydrogen, because that's what I'm looking for, the percent of hydrogen. And the whole thing is going to be the water, because that's what I want the percent of the hydrogen in. So this is what I would do. I would say, all right, we know H, there's 2 of them, times 1 is 2. You've seen me do this a million times. Okay? The whole thing is going to weigh 18 grams per mole. What is the part weigh? 2. What does the whole thing weigh? 18. The whole thing, not the 16, the whole thing weighs 18. So now we can say the part that is hydrogen, I'm going to put a little H there so I know that it's part that's hydrogen, is going to be 2 divided by the whole thing, which is 18 times 100. That's going to give me the part, or the percent that is hydrogen. And through my very fabulous calculator brain, I'm going to write down 11.1%. Okay, you check that on your calculator. Make sure you get 11.1%. Jaden, wake up. 11.1?
Yep.
Okay. That's how much hydrogen I have there. So, let's say I have a basket or a bucket of water. This is a bucket of water. Here's blue. Okay. How much water is in that bucket? Give me a number.
100 grams.
No, give me a better number. I don't like 100 grams.
1,000 grams.
I'm going for something that's not... All right, let's do 100 grams. 100 grams. Whatever. Okay? 100 grams of water is in that bucket. If I know that 11.1% of that bucket is hydrogen, how many grams of hydrogen do I have in that bucket?
About
11.1 grams. Because 11.1% of the 100 grams is going to be 11.1 grams. If I had another number that's not a nice easy number like this, let's say 758, grams of water in that bucket, how much of that is going to be hydrogen? What is 11.1% of 758 grams? Since I just made that up, I don't know it off the top of my head.
Like 77.
I need a calculator that actually works. Is it 84? 84 grams is going to be hydrogen. Now let's go back and figure out how much oxygen. What, are you lost, Cordy? You got it? Do you understand it? Okay. So now this is the percent that's hydrogen. What's the percent that's oxygen? The percent that's oxygen is going to be the part that's oxygen, P part O oxygen, over the whole thing times 100. What part was oxygen? Oh, that's the answer. What's the part that's oxygen? You gave me the answer. 16. What's the whole thing weigh? 18 times 100. And you got 88.9% oxygen. You just went ahead of us. Okay? So now, if that is the percent that's oxygen, how much of this 758 grams is oxygen? Good job. Go ahead. How do you find this percent? Okay, so let's go back. In order to find a percent, you're going to do the part of whatever the percent you're looking for. So if I'm looking for the percent of oxygen, you're going to find the gram formula mass. So here's the gram formula mass. If I'm looking for the part or the percent that's oxygen, the part that's oxygen is the 16. And then I divide that by whatever the whole thing weighs. 16 divided by 18 times 100. Put your hand down. I can't see your mouth. Oh, okay. So how do you find the percent of another number? Whenever you see the word of, you're going to multiply. So 88.9% of $758 or 758 grams, you're going to take 88.9, change it to a decimal, 0.889, and multiply it by that number, times. Anytime you see the word of, you're multiplying. So let's say you go out to dinner, right? And you get a bill. So here's the bill. And you had a hamburger. And then you had, I don't know, a hot dog. All right, and this was $10 and this was $4. All right, you got to leave a tip. What percent tip are you going to give them? 20% tip is standard, right? So your bill was $14. What's 20% of $14? Say it again. Yeah. Okay? Because you're going to take 0.2 of multiply 14. Okay? So 0.2 times 14 equals 2.8 or $2.80 is what you should be leaving for your tip. Okay? Questions? You good? Just happened to be 20% is a nice easy number. So does that answer your question? What was your question? How do you find the percent of something? Okay. So that's what I'm here for. If you have a question, you need to stop me and you have to say, how did you do that? So now we know that in water, 11.1% of it is hydrogen, and 88.9% is oxygen, right? Now, if I have a swimming pool full of water, can I find out how many grams of hydrogen I have? Sure, because I know 11.1% of whatever it is in that swimming pool is going to be hydrogen, and 88.9% of whatever it is in that swimming pool is going to be oxygen. Okay? So these percentages are going to help us out in the next step. Everybody good? We're losing Jade. You good? You know how to do all this? All right, sodium chloride. What's the percent of sodium and what's the percent of chlorine? And you can leave them as whole numbers. You don't have to put the decimal on there because it's going to come out nice and neat for you. Give me the percent of sodium and the percent of chlorine. I know you guys got the answer now, but I'm going to do the math out just so that everybody on tape can see it if you need to watch it again. Okay, so sodium and chlorine, we know that they're going to weigh 58 grams per mole. I'm going to do the percent that's sodium. So that's going to be the part that's sodium over the whole thing times 100. The part that's sodium was 23. The whole thing weighed 58. And I'm going to multiply it by 100, and I'm going to get 40 point something percent. I'm going to make it 40%. 40% sodium. Now, you know that the whole thing needs to be 100%. So 100 minus 40% should give us the 60 for the chlorine. Let's just make sure. Chlorine, the part that's chlorine over the whole thing times 100. The part that's chlorine was 35 divided by 58 times 100 equals, and then 60% for this chlorine. Okay? So if I hand you a bag of salt, let's just say I hand you a bag of salt. Here's a bag. And it says 49 grams. How much of that bag of salt is sodium, and how much of that bag of salt is chlorine? What is the number of grams of sodium and the number of grams of chlorine? Yeah, it was 60. So we're going to take, let me just finish writing it down. 40%, you're right, of 49, this is what you were asking me before. 40% of my salt is sodium. So 40% of 49 grams is 19.6 grams of sodium, and 60% of 49 grams is, and what did you say that one was? 29.4 something? Oh, hold on, I'll do it on the calculator. We got 0.6 times 40. I made these numbers up, so 29.4. Is that right? That sounds about right. Grams of chlorine. So this bag size doesn't really matter. I can figure out how many grams I have. Everybody got that? Okay, moving on. Okay. Let's do CuSO4. 5 H2Os. Oh, that's how I feel. You can. It's not that hard. You can do this. This is called a hydrate. Okay? It is a hydrate because you've got a salt attached to 5 water molecules. That's what that means. In math, this little dot means multiply. In science, this little dot means attached to. I'm going to draw it for you so that you can get a visual of what it looks like. Okay? Do you know what CuSO4 is called? What's that name of that? Copper Copper.
What do you find salts again?
Copper 2 sulfate. Okay?
What do you find salt?
Salts?
Yeah, what do you find?
Salts are a metal and a nonmetal, or a metal and a polyatomic ion. They are ionically bonded. There's an ionic bond right here between the copper and the SO4.
How do you know it's two?
Okay, let's hold on. Let's back up because it's going to be on the midterm. All right. So let's take just the copper sulfate, right? You know that this is copper, and you know that this is sulfate. Okay. When you look at copper on your periodic table, so take a little gander over at your periodic table, find copper. Put your finger on it. Okay? In the upper right-hand corner, there are two numbers. There's a +1 and a +2.
How do you know that one?
Hold on. Do you understand that there are two numbers there? If there are two numbers, there has to be a Roman numeral here. Okay? Which one of those Roman numerals, 1 or 2, is the one that was used to make the copper sulfate? It's the 2. Now, this is how you know. Okay? The sulfate, don't go anywhere. I'm almost done. The sulfate is a -2 charge. So what did the copper have to be? A +2. So this had to be a copper 2 sulfate. Okay? All right, take a little breaky and come back. We got more work to do.